Robots are increasingly used in many industries in the whole world, from healthcare and manufacturing to defense and education. For instance, a certain robot is being used in an industry or establishment to do a particular activity. Suppose that the statements described here are the routine for such robot to control activity in a warehouse. So we have statement number 1. Every robot has at least 2 paths. Statement number 2. Every path has at least 2 robots. And statement number 3. A minimum of 1 robot exists. In this set of statements, which do you think are terms that need to be defined? Suppose you are asked to prove another statement. Say, a minimum of 1 robot exists. Can you use these 3 statements to prove it? The set of statements here are true and contain terms that are undefined or needs to be defined. These statements can be used to create and to prove another statement. This set of statements are examples of an axiomatic system. An axiomatic system is a logical system which possesses an explicitly stated set of actions from which theorems can be derived. From the definition, you could say that axiomatic system consists of some undefined terms, also called the primitive terms, defined terms, list of axioms or postulates concerning the undefined terms, a system of logic or proofs to be used in deducing new statements called theorems. The axiomatic system or the axiomatic structure of a mathematical system can be compared to a tree. The ground is not part of the tree, but it is necessary for the tree to be planted and to grow. Like the ground, an axiomatic system needs a logical system of rules that allows one to make inferences. The roots at the base of the tree correspond to the undefined and defined terms of the system. These are the basic terms from which statements in the axiomatic system are made. Like the tip roots combine to build up roots of the tree, undefined terms are the starting point for every definition and statement of the system. They are combined in various ways into a statement called the definitions. Terms are defined for us to be precise and concise on its meaning. But there are some basic terms of the system that are necessarily left undefined. When we define a term, we will be using different terms that we also need to define. The trunk of the tree corresponds to the axioms or postulates, while the branches growing out of the trunk are the theorems. Axioms are the statements that serve as a starting point for the system. Axioms are the basic truths, and we use them to prove other statements. Theorems, on the other hand, are statements deduced from the axioms. Now, here are some properties of axiomatic system. The first one is consistency, the second one is independence, and the third one is completeness. Now, let us first discuss consistency. Consistency. An axiomatic system is said to be consistent if there are no axiom or theorem that contradicts each other. This means that it is impossible to derive both a statement and its negation from the axiom set of system. Now let's have an example. We have here the axiom statement. There exist 2 lines that are parallel. And the negation for this statement is that No two lines are parallel. Notice that the negation is not an axiom nor a theorem. The system where a statement and its negation are both true is said to be inconsistent. Therefore, an axiomatic system should be consistent for it to be logically valid. This means that there are no axiom or theorems that contradict each other. Otherwise, the axiomatic system is faulty or inaccurate. Now let's move on to the second property of axiomatic system, and that is independence. Now let's discuss independence. In an axiomatic system, an axiom or postulate is said to be independent if it is not a theorem that follows the other axioms. It is not a theorem that can be derived or cannot be proven true using other axioms in the system. For instance, you have four different axioms. If you can make a model showing that one axiom is independent of the other, that is, you cannot use the other three axioms to prove such axiom. Then, the axiom is independent. An example to this is Euclid's fifth postulate. Many people try to prove this axiom using the other four postulates, but either failed or used faulty reasoning. This problem led to the development of other geometries, where the fifth theorem of Euclid was shown to be independent of the other postulates. Independence is not necessary requirement for an axiomatic system. Now let's proceed to the third property of axiomatic system, and that is completeness. Completeness. An axiomatic system is complete if for every statement, either itself or its negation is derivable in that system. In other words, every statement is capable of being proven true or false. Now that you have learned the axiomatic system, let us try to apply it in the situation mentioned earlier about the artificial axiomatic system describing a routine for a computer to control activity of the robot in a warehouse. The set of axioms given were these statements. Statement number 1, every robot has at least two paths. Statement number 2, every path has at least two robots. And statement number 3, a minimum of one robot exists. Now, if we are going to answer the question, what are the undefined terms in this axiom set? From these three statements, we can see that the undefined terms are robot, path, and has. The terms robot and path are elements and the term has is a relation. This indicates that there is some relationship between robot and path. These undefined terms can be used to build construct to various proofs. Now notice that axiom 3 or statement number 3 is a consequence of axiom or statement 1 and statement 2. The example clearly shows that an axiomatic system is a collection of axioms or statements about undefined terms from which proofs and theorems or logical arguments are built. Now let us have some examples and illustrations of each part in the axiomatic structure. There are four parts in the axiomatic structure. The first one is what we call the undefined terms. Second one is the defined terms. The third one is the axioms. And the last one are theorems. Now let us first discuss undefined terms. Axiomatic structure started with three undefined terms or primitive terms. These are point, line, and plane. These terms are the basis in defining new terms, hence they are called the building blocks of geometry. Even though they are called undefined terms, it does not really mean that we are restricted to describe or represent them. Now, the table here shows the different ways of describing these three undefined terms. So we have the definition of point here. Point is something having specific position, but it has no dimension, no length, no width, and no thickness or direction. A point can be represented with a dot and is denoted by a capital letter. The 2 points below are point A and point B. Now, let's have here line. A one-dimensional figure with infinite numbers of points, no specific length, without width nor thickness. It is always straight that extends indefinitely in two opposite directions. The line below is line AB, denoted by the symbol line AB, which is named after the 2 points that are on the line. Lines can also be denoted by a lowercase letter, like line L below. Now let's proceed to plane. Plane is a flat surface where infinite numbers of lines can lie. It has no specific length and width and without thickness. It extends indefinitely in all directions. The parallelogram below is a plane denoted by the Greek letter A, read as alpha. This plane can also be named as plane A, B, and C. Now, there are objects that illustrates point, line, and plane in real world. In your previous activity, they are tip of a pencil, tip of a marker, corner of a rectangular tray. These three examples or objects are example of a point. Now, on the second column rather, we have here edge of a cabinet, edge of a book, stretched rope, and edge of a ruler. Now, these are also examples of objects that illustrate line. Now, in the last column, we have here objects in real world that illustrates plane. First is top of the table, second one is wall of a classroom, and the third one is cell phone screen. Now, let us proceed to the second part of the axiomatic structure, which is the defined terms. Now, let us discuss defined terms. From three undefined terms, important concepts in geometry will be defined. Remember that we need defined terms because we want to be precise and concise on the meaning of a term. Definitions will enable us to understand each other and to make sure we mean the same thing about a certain term. Now, here are some definitions derived from the undefined terms point, line, and plane. We are going to discuss all 23 definitions, and let's start with definition of a segment. Segment AB, denoted by the symbol segment AB or segment BA, is the union of 2 points or points A and B, and all the points between them. A and B are called the endpoints of the segment. So we have here the the endpoint A and the endpoint B. When you connect 2 points, this becomes a segment. So the point A is our first endpoint and the point B is our second endpoint. Now let's proceed to definition of between. Point U is said to be between F and N. if and only if F, U, and N are distinct points of the same line and FU plus UN is equal to Fn. So this is our line, F and N, and it says here point U is said to be between F and N. So between F and N, we have here point U. If and only if U and N, F, U, and N are distinct points of the same line. They are different points, but they are on the same line. And Fu plus Un is equal to Fn. In line Fn, U is between F and N. Since F, U, and N are distinct points on the same line, and Fu and is equal to Fn, and 2 cm plus 3 cm is equal to 5 cm. Now let's proceed to definition of collinear points and coplanar points. When points are on the same line, they are called collinear points. So I have here the figure with line AC and points B and D. Note that points A, B, and C are on the same line. Hence, they are said to be collinear, while point B is not on the same line with the other three. Thus, these 4 points A, B, C, and D are non-collinear. Now let's proceed to coplanar. When points are on the same plane, they are called coplanar points. Notice that points B, I, G are on the same plane B. Hence, they are said to be coplanar. The fourth one is what we call the definition of a ray. Ray is a part of a line that has one endpoint and goes on infinitely in one direction. I have here a figure. Notice that in this figure, ray AB starts from point A and goes on to the right without bound. A is called the endpoint of ray AB. And the fifth definition is what we call definition of an angle. An angle is the union of two non-collinear rays with a common endpoint. So I have here the figure. We have here ray EB and ray ED. The common endpoint is endpoint E. So the common endpoint being shared by ray EB and ray ED is point E, and this is what we call the vertex. The angle formed could be named as angle 1 because we did put a number here, which is 1, or angle BED or angle DEB. Now let's proceed to the sixth definition. We have here definition of congruent angles. Two angles are congruent if and only if their measures are equal. In symbol, angle X is congruent to angle Y if and only if the measurement of angle X is equal to the measurement of angle Y. So in figure, we have here two angles. This is angle X and this is angle Y. Now the basis of their congruency is their measurement. So the measurement of angle X is 45. So the measurement of angle Y is also 45 degrees since both angles are congruent. Now let's proceed to the seventh definition, which is definitions of acute angle, right angle, and obtuse angle. An acute angle is an angle with a measure greater than 0 degrees but less than 90 degrees. A right angle is an angle with a measure of exactly 90 degrees. And the last one is the obtuse angle. An obtuse angle is an angle with a measure greater than 90 degrees but less than 180 degrees. Here are their figures. First, this is what we call acute angle. So the measurement here from ray BA to ray BC, the measurement is less than 90 degrees. Greater than 0 degrees but less than 90 degrees. While right angle here has a measurement of exactly 90 degrees. That is why we have this symbol to indicate that this angle has a measurement of exactly 90 degrees. While the obtuse angle, the measurement from ray BA to ray BC is greater than 90 degrees but less than 180 degrees. Now let's proceed to the eighth definition, which is definition of adjacent angles. Adjacent angles share a common vertex and a common side, but these angles do not overlap. Now let's have this first figure, angle ABD and angle CBD. These are adjacent angles which have a common vertex B and a common side ray BD. The interiors of angle ABD, this one in green, do not intersect with the interiors of angle CBD, this one in black, and these two angles have no interior points in common. That is why these two angles are adjacent angles. Now let's proceed to the other figure. So I have here angle EFG and angle GFH. Both angles have F as common vertex and ray FG as a common side, but the interiors of the two angles intersect. This means that the two angles have common interior points. Thus, angle EFG and angle GFH are not adjacent angles. Now, let's proceed to the definition of supplementary angles. Two angles are supplementary when the sum of their angles is 180 degrees. Now, I have here figure or angles ABD and angle DBC. Notice that angle ABD, we can name that one as angle 1 and angle DBC as angle 2. Now, these two angles are supplementary when the measurement of angle 1 and the measurement of angle 2 is combined, comes up with a total of 180 degrees. Now, when we separate these two angles, this becomes like this. So we have angle ABD rather, or angle 1 with a measurement of 120 degrees, and angle DBC or angle 2 with a measurement of 60 degrees. Now, if we combine 120 and 60 degrees, this has a total of 180 degrees. That is why angle ABD and angle DBC are supplementary angles. Now, let's proceed to the definition of linear pairs. A linear pair of angles is formed when two lines intersect. Two angles are said to be linear if they are adjacent angles formed by two intersecting lines and are supplementary. So we have here the figure. Ray BD is the common side and ray BA and ray BC are opposite rays. So angle ABD and angle CBD forms a linear pair. Now let's proceed to the 11th definition, which is definition of vertical angles. Opposite angles formed by two intersecting lines that are vertical angles. So we have here the figure. That is angle 1 angle 2, 3, and 4. Angle 1 and angle 3 are vertical angles. Also, angle 2 and angle 4 are vertical angles. Notice that these angles are opposite to each other. Because of the definition, opposite angles formed by two intersecting lines are what we call vertical angles. Now let's proceed to the 12th definition, which is the definition of perpendicular lines. Perpendicular lines are two lines that intersect to form a right angle. So we have here line AB and line CD. So the point of intersection is point E. Line AB intersects line CD at point E. Angle AED, angle AEC, angle BEC, and angle BED are right angles formed by these two intersecting lines. Hence, line AB is perpendicular to line CD. In symbols, we have here line AB is perpendicular. This is the symbol for perpendicular to line CD. Now let's proceed to the definition of perpendicular bisector. A perpendicular bisector, PR, of a line segment XZ is a line segment perpendicular to XZ and passing through a midpoint. So this is our segment PR and segment XZ. And the point of intersection is point Y. Segment PR is perpendicular to segment XZ at point Y. Segment PR divides segment XZ into two equal parts. Thus, segment XY is equal to segment ZY. Furthermore, segment XY is congruent to segment ZY. Now, let's proceed to the 14th definition, which is definition of a polygon. A polygon is a closed figure such that the union of three or more coplanar segments which intersect at endpoints shared by exactly two non-collinear segments. So I have here pictures of polygons. These are polygons: triangle, quadrilateral, pentagon, hexagon, heptagon, octagon, nonagon, decagon, and so on and so forth, as long as it is a closed figure. Now let us proceed to the definition of convex polygon. A polygon is convex if and only if the lines containing the sides of the polygon do not contain points in its interior. For example, we have here this figure. So we have here point A, point B, point C, and point D. These 4 points are what we call the points of intersections. Now, inside is what we call the interior, since point B to point C to point D to point A, and point A to point B forms a polygon, and its interior does not contain points. Therefore, polygon A, B, C, and D is what we call a convex polygon, because inside it, this is so considering only polygon A, B, C, D, we can see that there are no points in its interior. So therefore, we can conclude that this polygon is a convex polygon. Now let's proceed to the definition of a non-convex or the concave polygon. A polygon is non-convex or concave if and only if at least one of its sides is contained in a line, which contains also points in the interior of a polygon. Now I have here the figure. line LM, this one is what we call line LM, which contains line segment LM, also contains points in the interior of the polygon. As you can see, we have here the broken line, but this represents points which passes through the interior of the polygon JKLM. Therefore, this is a concave polygon because there are points that passes through the interior of the polygon J, K, L, and M. Now let's proceed to the 17th definition, which is the definition of a regular polygon. So we have here a regular polygon is a polygon that is both equilateral and equiangular. When we say equilateral, this means equal sides, and equiangular means equal angles. Now we have here the polygon, the regular polygon DREAM, DREAM. The regular polygon DREAM has 5 interior angles. These are the 5 interior angles: angle RDM, angle ERD, angle AER, angle EAM or MAE, and angle DMA. So these are the 5 interior angles, and these angles are equal. Also, the polygon DREAM has 5 equal sides. Sides DR, RE, EA, AM, and MD. These 5 sides are equal. Point O here is the center of the polygon. So angle O is the central angle. Regular polygon DREAM also has 5 exterior angles. These angles are obtained when one of the intersecting sides is extended, such as angle AMN. The outside angle along with the vertex is an exterior angle. This one, the one in brown, is what we call the exterior angle. Now let's proceed to the 18th definition, which is the definition of a triangle. A triangle is a three-sided polygon. So here is an example of a triangle. This is triangle NEP. Now, the symbol, this symbol, followed by 3 letters representing the non-collinear points or the vertices, this is what we call the vertices, is used to name the triangle. Every triangle, like triangle NEP, has 3 sides, 3 angles, and 3 vertices. The 3 sides are side NE, side EP, and side NP. Also, the angles are angle N, angle E, angle P. And the vertices are also vertex N, vertex E, and vertex P. Now let's proceed to the 19th definition, which is the definition of angle bisector of a triangle. An angle bisector of a triangle is a segment contained in the ray which bisects the angle of the triangle, and whose endpoints are the vertex of this angle and a point on the opposite side. Now I have here the figure or the triangle LOV. Now, segment OE is an angle bisector of triangle LOV. It is the bisector of angle LOV, and the endpoint O here of the angle bisector is the vertex of triangle LOV, and the other endpoint E is on the opposite side. Thus, angle LOE is congruent to angle OV. Let's proceed to the definition of an altitude of a triangle. A segment is an altitude of a triangle if and only if it is perpendicular from a vertex of the triangle to the line that contains the opposite side. So I have here this figure. Every triangle has three altitudes. In triangle STA, segment TY is one of the three altitudes. Now let's have another figure. In triangle SAF, line segment SE is one of the three altitudes. Now let's have another one representing the three altitudes. In triangle LSE, line segment LI and segment SN and also the segment TE are the three altitudes. Now let's proceed to the 21st definition, which is the definition of a median. A segment is a median of a triangle if and only if its endpoints are a vertex and the midpoint of the opposite side. So I have here triangle NRA. Every triangle has also three medians. Median except its endpoints is always in the triangle's interior. Unlike altitude that can be drawn from the exterior of the triangle, line segment AO is the median to segment NR, and line segment RL is the median to line segment NA, and of course, line segment NM is the median to line segment AR. Notice that the distance between segment OR and segment ON is congruent, as well as the distance of segment RM and segment MA, and also the distance between segment NL and segment LA are also congruent. Now let's proceed to the definitions of acute, right, obtuse, and equiangular triangle. An acute triangle is a triangle in which all angles are acute. A right triangle is a triangle in which one of the angles is a right angle. An obtuse triangle is a triangle in which one of the angles is obtuse. And an equiangular triangle is a triangle in which all angles are congruent. These were discussed in the previous definition that acute, right, and obtuse has different measurements, also equiangular. Now, in acute triangle, all angles are acute, meaning all the angles of an acute triangle has a measurement greater than 0 degrees but less than 90 degrees. While a right triangle here states that one of the angles, meaning 1/3, has a measurement of exactly 90 degrees. While an obtuse triangle here also states that one of the angles is obtuse. So, one of its sides or angles has a measurement greater than 90 degrees but less than 180 degrees. But an equiangular triangle is a triangle in which all angles are congruent. The measurement of three angles in an equiangular triangle are congruent with a total of 180 degrees. Now let's proceed to the final definition that we have. Definitions of scalene, isosceles, and equilateral triangle. A scalene triangle is a triangle with no congruent sides. An An isosceles triangle is a triangle with at least two congruent sides, and an equilateral triangle is a triangle with all sides congruent. So scaling, the measurements of the sides of the triangle are different, and in isosceles, two sides of a triangle has the same measurement, while equilateral triangle has a measurement that is equal on all three sides. Now let us continue to the third part in the axiomatic structure, which is the axioms. Now let's discuss axioms. Axioms. Axiom is a logical statement accepted to be true without proof. Axioms can be used as a premise in a deductive argument. In the Elements, Euclid presented 10 assumptions, 5 of which are not specific to geometry, and he called them common notions, while the other 5 are specifically geometric, in which he called them postulates. Now, the following are examples of common notions. Axiom 1, we have here transitive property of equality. Axiom 2, addition property of equality. Axiom 3, we have here subtraction property of equality. Axiom 4, reflexive property. And axiom 5, we have here axiom 5.1, symmetric property of equality. And axiom 5.2, we also have here substitution property of equality. Now let us first discuss the first axiom, which is the transitive property of equality. Axiom 1, transitive property of equality. Things which are equal to the same thing are also equal to one another. This is transitive property of equality. So we have here the figure. If A is equal to B and B is equal to C, then A is equal to C. So we have here the measurement of line segment AB is equal to 12 cm and CD is equal to line segment AB. Therefore, line segment CD is also 12 centimeters. Now let's proceed to the second axiom, which is addition property of equality. Now let's discuss axiom 2. Axiom 2. Addition property of equality. If equals are added to equals, the wholes are equal. This is addition property of equality. In figure, we have here, if A is equal to B and C is equal to C, then A plus C is equal to B plus C. So we have here, if the measurement of segment AB is 4 cm, and that is equal to the measurement of segment DE, which is also 4 cm, and the measurement of segment BC is 3 cm, and the measurement of segment EF is also 3 cm, then segment AB plus BC is equal to 7 cm, as well as segment DE and EF is also equal to 7 cm. Since line segment AB is equal to line segment DE and line segment BC and line segment EF, and if A plus B plus B plus C or segment DE plus segment EF, then segment AC is equal to segment DF. That is 4 cm plus 3 cm is equal to 4 cm plus 3 cm. Now both expressions comes up with the same answer, which is 7 cm. So we have here 7 cm is equal to 7 cm. Now let's proceed to the third axiom, which is subtraction property of equality. Now let us discuss axiom 3. Axiom 3. Subtraction property of equality. If equals are subtracted from equals, the remainders are equal. This is subtraction property of equality. So in figure, we have here, if A is equal to B and C is equal to C, then A minus C is equal to B minus C. So we have here in numbers, we have, since line segment AB is equal to line segment DE, and line segment CB is equal to the line segment FE, and if line segment AB minus line segment CB is equal to line segment DE minus line segment FE, then line segment AC and line segment DF is equal. And that is 9 cm minus 4 cm is equal to 9 cm minus 4 cm. And both has the same answer, and that is equal, which is 5 centimeters. Now let's proceed to the fourth action, which is reflexive property. Now let's discuss reflexive property. Reflexive property. Things which coincide with one another are equal to one another. This is reflexive property. In figure, let's say, if the triangle in B fits to the triangle in A, then the triangle in A is equal to the triangle in B. Or, in different figure, segment OR is congruent to segment OR. Then, OR, segment OR, the measurement of segment OR, is equal to the measurement of segment OR. Any segments, angles, and polygons are always equal to themselves. Now let's proceed to the next action, which is action 5.1, symmetric property of equality. Now let's discuss symmetric property of equality. Action 5 states that the whole is greater than the part. Now, for all real numbers P and Q, if Q if P is equal to Q, then Q is equal to P. We have here the figure. So if P is equal to Q, then Q is also equal to P, because both are equals or symmetric. Now let's discuss the next action, which is substitution property of equality. The substitution property of equality states that for all real numbers P and Q, if P is equal to Q, then Q can be substituted for P in any expression. For example, we have here, if this is angle P that is congruent to angle R, and angle Q is supplementary to angle P, then angle Q is also supplementary to angle R. Now let us discuss geometrical postulates. I have here postulate 1. A straight line segment can be drawn joining any two distinct points. So, I have here 2 points A and B. If we connect them, this will make us a line segment AB. Or a line segment AB can be drawn if you have 2 points, like point A and point B. Now let's proceed to postulate number 2. Any straight line can be extended indefinitely in a straight line. So we have here line segment CD, and this line segment CD can be extended indefinitely in both directions. Let's proceed to the third postulate. Given any straight line segment, a circle can be drawn having the segment as a radius and one endpoint as center. So we have here a line segment CD. From line segment CD, we can draw a circle by using the measurements or the measure of line segment CD as the radius and point C or this endpoint as a center. Now let's proceed to postulate number 4. Postulate number 4. All right angles are congruent. So we have here angle 1 and angle 2. Angle 1 and angle 2 are right angles. Why? Because of this symbol. The measurement of angle 1 is equal to the measurement of angle 2, which is equal to 90 degrees. Hence, angle 1 is congruent to angle 2. Now let's proceed to postulate number 5. If a straight line meets two other lines so as to make the two interior angles on one side of it together less than two right angles, the other straight lines will meet if produced on that side which the angles are less than two right angles. So we have here the figure. Line L meets two other lines M and N. Then angle 1 and angle 2 are interior angles formed on the left side of line L. Now, if we are going to shade this will become the measurement of angle 1 plus the measurement of angle 2 is less than 180 degrees. When extended on this side, lines M and N, so see M and N, this is line M and this is line N, meets at point P. So they have a point of intersection which is P. The angles formed are less than 180 degrees. So the measurement of this angle is less than 180 degrees. This is what postulate number 5 discussed. Postulate number 5 asserts that two distinct straight lines in a plane are either parallel or meet exactly in one point. Here. So we have line AB is parallel to line CD. So in symbol, we have this symbol as parallel. Also, we have here line EF intersect with line GH at point R. Hence, the lines are not parallel. So the symbol for not parallel is this one. Now let's proceed. Postulate number 5 is referred to as parallel line postulate. The following are other postulates about point, line, plane, and figures formed by this and the basic postulates. So we have this one first. If two distinct planes intersect, then their intersection is a line. So we have this figure. We have two planes, plane P and plane R. Now, when they intersect, their point of intersection is line L. Now, let's proceed to the second one. If two points of a line are in a plane, then the line containing these points is in the plane. So this is postulate number 5 also. We have here the figure. A line that lies in a plane divides the plane into two subsets, each of which is called a half plane. The dividing line is called the edge. So line L here is what we call the edge. Points S and P of line L are on plane A, and therefore line L is in plane A. Now let's discuss the segment addition postulate. If points P, Q, and R are collinear and point Q is between points P and R, then PQ plus QR is equal to PR. Also, this is under postulate number 5. So, this is the same with our definition earlier, definition of between. So, this is also called segment addition postulate. So, segment PQ is equal to 2 cm and segment QR is equal to 3 cm. When you combine the two segments, the total is 5 cm. So that is also line PR. Let's move on to angle measurement postulate. To every angle, there corresponds a unique real number R, where R is greater than 0 but less than 180 degrees. And also under postulate number 5, geometry angles are measures in units called degrees. In symbol, this is a symbol for degree, an angle φ is 45 degrees. In notation, if we are going to write this in notation form, this is how we write this. The measurement of angle FUN is equal to 45 degrees. Now let's proceed to the last postulate that is under postulate 5. The addition or the angle addition postulate. Angle addition postulate, this is what we call angle addition postulate. Two angles with a common side and a common vertex, when you add those measurements, that is what we call angle addition postulate. So in the figure, the measurement of angle SAE is equal to the measurement of angle SAV and the measurement of angle VAE. So we have here 15 degrees plus 45 degrees is equal to 60 degrees. That is what we call angle addition postulate. Now let's proceed to the fourth part in the axiomatic structure, which is theorems. Theorems are the new statements which are deduced or proved using sets of axioms, system of logic, and previous theorems. These are statements accepted after proven deductively. So, let us have some theorems about points, lines, and planes. So we have here theorem number 1. If two different lines intersect, then they intersect at exactly 1 point. So we have here line A and line B. Their point of intersection is point A. Now let's discuss theorem number 2. If a line not contained in a plane intersects the plane, then the intersection contains only 1 point. So here is our illustrative example. We have here plane Z and line L. If a line not contained in a plane intersects the plane, so ning lahos ra si line L, then the intersection contains only 1 point. So their point of intersection is only point Y. This is theorem number 2. Now let's proceed to theorem number 3. Theorem number 3. If a point lies outside a line, then exactly one plane contains both the line and the point. So this is our illustrative example. When we have 1 point and one line, then this point and a line is contained in exactly one plane. So if present lang ang 1 point and one line automatic, they are contained in a plane. Now let's proceed to theorem number 4. Theorem number 4, if two distinct or different lines intersect, then exactly one plane contains both lines. So we have here the illustrative example. We have line D and line E. They both intersect and their point of intersection is point S. So these two lines and the point of intersection is located at exactly one plane. That is theorem number 4. Now let's proceed to the next theorem, which we call the linear pair theorem. If two angles form a linear pair, then they are supplementary. This is the illustrative example. If we have opposite rays and a common side and a common vertex, therefore the angles of the two angles formed are supplementary. Now let's proceed to vertical angles theorem. Vertical angles theorem states that vertical angles are congruent. So the measurement of the angles are congruent. For example, in this illustrative example, two lines M and L intersect, forming two pairs of vertical angles. Angle 1 and angle 3, angle 2 and angle 4. Hence, the measurement of angle 1 is congruent to the measurement of angle 3, and also angle 2 is congruent to angle 4, since angle 2 and 4 are vertical angles. Now let's proceed to perpendicular bisector theorem. Point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. So, since x, the line segment xy, is congruent to line segment zy, then y is equidistant from the points x and z, meaning y is in between x and z, showcasing equal distance from 2 points. That is perpendicular bisector theorem. Now let's proceed to isosceles triangle theorem. Base angles of isosceles triangles are congruent. So we have here the illustrative example. If line segment AB is congruent to line segment CB, then angle A is congruent to angle C. If these two sides are congruent, then the angles opposite to the sides are also congruent. Now let's proceed to the exterior angle theorem. The exterior angle of a triangle is equal to the sum of the two remote interior angles of the triangle. The exterior angle of a triangle is greater than either of the measures of the remote interior angles. So we have here the illustrative example. Angle B and angle D are the remote interior angles of the triangle. So the measurement of angle C is equal to the measurement of angle B plus the measurement of angle D. And also, the measurement of angle C is greater than the measurement of angle B, and also measurement of angle C is also greater than the measurement of angle D. This is what we call the exterior angle theorem. Now the next one, or the last theorem we have, is triangle angle sum theorem. The sum of the measures of the angles of a triangle is 180 degrees. So we have here the illustrative example, angle 1, 2, and 3. The measurement of angle 1 plus the measurement of angle 2 plus the measurement of angle 3 is equal to 180 degrees. That is what we call the triangle angle sum theorem. Now that you have learned the definitions, postulates, and theorem, you are now ready for the next activities. Thank you for watching and see you on the next video.